Hello everyone, I'm going to present our work end-to-end speaker diarization system for the third DIHARD challenge. I'm the presenter, Leung. Another author is Nahiro Samara-Kong. We are from Fano Labs, Hong Kong. First, we will give an introduction of our work. Secondly, we will talk about our proposed system. Then we will talk about our dataset we used. Finally, we will share the experimental result. First, our model is based on the recent self-attentive end-to-end diarization model with encoder-decoder-based attractor. The model architecture is illustrated in this figure, which is from the original paper. And in this challenge, we focus on threat 2 because the end-to-end model is capable of handling speech activity detection internally. We proposed 5 modifications on the original end-to-end system. First, we use conformer encoder instead of transformer encoder. Secondly, we use a convolutional upsampling module to upsample the result resolution. Then, we incorporate the attention into attractor calculation. Next, we also introduce the additive margin penalty into the speaker diarization result calculation. Finally, we try to shuffle different chunks in order to increase the combination of audio samples. Conformer is proposed in the recent Conformer Convolution Augmented Transformer for Speech Recognition paper. The main component is the conformer box, which combines the transformer and convolutional network. The transformer is good at handling the global feature, but it is bad at handling the local features. So we want to use the conformer box to replace the transformer encoder in order to handle the local feature. Next, we observe that each frame in the original end-to-end model is about 0.1 second because it subsampled the input feature by a factor of 10. But in the DIHARD evaluation, no caller is used. We find that when the result comes with a low resolution, it will increase the DER. So first we paste a convolutional upsampling module to increase the resolution of embedding. Then we, instead of manually subsampling the input feature, we use a convolution subsampling module here to subsample the audio feature by a factor of 10. Next, in the DIHARD challenge, we can observe the sequence of embedding is very long. And in the original end-to-end model, the information of the attractor is passed by the last timestamp of the encoder output and the cell state. So we suspect that some important information could be lost when the sequence is very long. So instead of using the last timestamp of the encoder to initialize X0 and C0, we use 2 separate multi-head attention as a pooling mechanism to initialize X0 and C0, which is illustrated in the left-hand side of the figure. The main component is the multi-head attention. We use the multi-head attention to aggregate the embedding to produce the X0 or C0. And also, we also use a common global attentional mechanism on the decoder side. It allows the model to retrieve the information from the embedding at each decoder timestamp. Next, inspired by the angular softmax, we try to put the additive margin penalty into speaker diarization result calculation to increase the difficulty of the task and make the model more robust. So basically, we first normalize all the attractor. Then we use the permutation event training to obtain the correct permutation of the speaker label, similar to the original paper. So after that, we will know whom the attractor represent. So in the real optimization step, the posterior probability of YTS hat of a speaker S at time t is calculated by this equation. Basically, the embedding at time t and the attractor of speaker S, we do the dot product, and with the speaker S at time t is 1, that means the speaker S speed at time t will give a minus m. Otherwise, we'll add a plus m there in order to increase the difficulty of the task. So finally, actually in the training procedure, each training sample is a 50-second audio from the original recording. So in order to increase the combination of different audio sample, we divide the original recording into a smaller pieces. It's about 10 seconds. Then we shuffle those pieces with a probability of 0.5. Here is the data set we used. First, we will create some simulated recording on the Libre speech dataset. Then we'll pre-train our model on those simulated recording. Then we'll fine-tune our dataset on the in-domain data. Here is our fine-tuning training set. In detail, we split our DIHARD 3 development set into a training set and validation set. Now I will share the experimental result on the conformer and the resolution. First, when we look at the DER, we can see when we use the conformer encoder, it gives significant improvement on the validation set and the evaluation set. Also, it also improved the JER. And in addition, we also tune the number of layers and the dimension of T10 unit. So the second column indicates the encoder has 7 layers and T10 unit dimension is 128 instead. When we use a deeper network, we saw some improvement on the validation set in DER. But the DER on the evaluation set does not give a big difference. But the model with three modification, it gives the best result on the evaluation set in DER. As it gives the best result on the DER on the evaluation set and validation set, validation set in DER. So we continue our development with these 3 modifications. And now we're going to share the result of the attention mechanism and the additive margin penalty. So basically, if we incorporate the attention mechanism into the attractor, it gives significant improvement against the model without attention mechanism. And when we also incorporate the additive margin penalty, it gives further improvement on our validation set in DER, as well as the JER on the validation set and evaluation set. Despite that, it does not give a big difference on the evaluation set DER. So we'll continue, we'll incorporate these 2 modifications in our system and continue to development our system based on these 2 modifications. Finally, we try to incorporate the Tsun shuffling during the fine-tuning process. We can see that on the evaluation set DER, on the full set, we can achieve 20.7 DER on the full set. When compared to the previous best system, it only achieved 21.7. That means the Tsun shuffling gives 1% DER improvement on the full set. And that means it proves the Tsun shuffling gives significant improvement. For the second column, larger input indicate that the pre-trained model is trained with a longer time. And when the pre-trained model is trained with a longer time, it also gives significant improvement here. And on the full set, on the evaluation set, we achieve 20.05. And this system is our final system. So in the future, we will give more detailed comparison of different modifications, and also we will try to train the pre-trained model with a longer time for comparison. Thank you.